you. Hello, everyone. Great to be here. I'm Shanfeng Zhu from Fudan University. I'm sorry I can't go to Montreal. My visa application is still under background check. So today I'm going to talk about our work on contig binning, which was published in Nature Communication in January. So from the previous keynote speech, we can say that there are several important metagenomic computational methods, including sampling, contig binning, and taxonomic annotation. Our work focuses on contig binning, which aims to group genomic fragments, that is the contigs from the same genome into the same bin. The commonly used binning method combines k-more frequency and coverage information. The most representative individual binning methods are Concord and MATBAT. So this method takes two kinds of information as input, obtain two kinds of distance or similarity through statistical method, then perform clustering to get a binning result, or concatenate two features for clustering. However, it's difficult for individual binning tool to achieve ideal performance on different types of data. The binning performance can be influenced by various factors, including dataset size, such as N15, the number of sequence sampling, and the number of contigs. To address the challenge of contig binning, there are mainly two different approaches. The first is to use ensemble approach to integrate the method using different features, such as k-more frequency and coverage information. And the second approach is to learn a better representation using deep learning. Previously, we have developed an ensemble method, MetaBinner, for improving the performance contig binning, which achieves good performance in CMI2 challenge. Today, we focus on the second approach. So to try to get a better representation by deep learning, there are two representative methods, CMB and SAMBin. CMB is a binning method that utilizes contrastive learning. Contrastive learning is a self-supervised learning technique used for learning an informative representation of the input data by bringing similar instances close together, where pushing dissimilar instances farther apart. CMB introduced a pair of augmented data for each contig by adding noise to the feature factor. However, simulate the data noise for the complex metagenome is difficult. CMB only has a slight improvement compared to variant without using contrastive learning. On the other hand, SAMBin is a semi-supervised binning method based on deep learning. It constructs pairwise mask-link constraints by splitting contigs longer than 4,000 base pair into two equal length segments and construct the pairwise concatenating constraint from the taxonomic annotation information. However, the quantity and the quality of the mask-link constraints are influenced by the length distribution of the contigs within the dataset. And also the concatenating link information is not very useful for the contig binning. So in this work, we propose ConBin, a contig binning method based on contrastive multi-view representation learning. The figure shows the workflow of ConBin. It mainly divided into four main steps: data augmentation, feature factor construction, contrast learning, and clustering. First, we introduced a data augmentation approach that generated multiple views for each contig, enable contrast learning, and generate high-quality representation of the heterogeneous features. Contiguous sequence fragment extracted from the same contig should belong to the same genome. So we randomly select 5 continuous segments of no less than 1,000 base pair for each contig to obtain 5 sets of augmented data. In this way, we obtain 6 views for each contig, including 1 original view and 5 views corresponding to the augmented data. Then ConBin construct k-more frequency and coverage features for each contig, including the origin sequence and augmented sequence. Specifically, a network named as the coverage network is deployed to derive embedded representation of coverage features. A network named combined network integrates two kinds of features and obtains embedded representation containing heterogeneous information through contrastive learning. By optimized contrast loss, the representation of similar instances are pulled close, where lots of dissimilar instances are pushed valid. In our task, fragments extracted from the same original contigs in the data augmentation step are pulled closer. In each training batch, the sequence fragments generated from different contigs are pushed valid. After obtaining the representation of the original contigs for the trained network, we use advanced community detection method laden for clustering. There are two differences between oversetting and the commonly used laden method. First, we assign a unique cluster for each contig as the initial membership, and the designated contigs contain a particular single copy gene as fixed members, ensuring that the contigs with the designated single copy gene are clustered into different clusters. The searching is motivated by the fact that the contigs that harbor the same single copy gene are derived from different genomes. Secondly, we set the load size of each contig using its length, regarding each load as an aggregation of a base pair of the contig. Combine achieved the best overall performance on the 16 datasets, including 10 simulated and 6 real datasets. For the CMI dataset, which are provided by the organizer of the second CMI challenge, Combine performs best on the 4 marine and plant associated datasets, especially on the marine GSA dataset. Combine increased the number of near-complete beans from 285 to 313.7 compared with the second best method. Regarding the stream madness dataset, no single method has a clear advantage. There are closely related strings in the stream madness dataset, which pose a challenge to the using the existing binning method to recover high-quality beans. For the sixth real dataset, Combine recovers about 22% more near-complete genomes on the average than the second best performance. Co-assembly and single sample binning are commonly utilized to benchmark the performance of a binning method. Recently, VMB and SMB1 introduced the multi-sample binning. In multi-sample binning, the sample-specific contigs are used for binning, but abundance information is aggregated across sample. We further show the performance Combine for single sample and multi-sample binning on 3 real datasets. In single sample binning, Combine recovers 33% more near-complete genomes than the second best binner. In multi-sample binning, Combine recovers 218% more near-complete genomes than the second best binner. We would like to show that Combine can be a valuable tool for analyzing metagenomic sequence data by integrating into the metagenomic analysis pipeline. Here is an example. Identify potential pathogenic antabolic resistant bacteria is crucial in microbiological risk assessment. Following the related study, a moderate or higher quality bean with at least one antabolic resistant gene and one variance factor gene is defined as a potential PRB. When integrated Combine into the PRB identification workflow, the number of potential PRB identified from the water group dataset has shown an average increase of 33% in comparison to the second best binner. So in summary, Combine is a binning method based on the multi-field contrastive learning. The contrastive learning approach aims to make the representation of different fields of the same contig as similar as possible, where ensure that the representation of different contigs are distinct, resulting in high discriminative embeddings. Results show that Combine outperforms the state-of-art of binning method, particularly in recovering near-complete genome from rare experiment samples. Combine can be a valuable tool for analyzing metagenomic sequence data and the research can integrate into the metagenomic analysis pipeline. Also, we have put the code in the GitHub, so you can use it. So that's what I want to talk about today. I would like to thank my student, Dr. Ziye Wang, and my collaborator, Professor Feng Zhu in the University of Southern California. For the details method, you can check our paper. And thank you for your attention.
Let's thank the speaker. Questions?
Hi there. Thank you for the talk. I'm curious about how this method does binning eukaryotic microbe sequences, and if you've checked any of those bins for fragmentation, or what the eukaryotic microbe situation is with this tool versus other tools.
Yeah, it's a very good question. I think in the CMI2 dataset, there is one dataset, maybe the plant related dataset. I think we did okay. I mean, because our method relies on the checkm to evaluate the performance. So for the eukaryotic species dataset, I think they don't have the single copy marker gene. So anyway, for the plant associated dataset, the result is okay, but it's not the best. I think the best is the metadecoder. Yeah. Is it okay for your question?
Yeah, thank you. And I also have a quick question. So especially for antibiotic resistance and other mobile elements, the KMER profile might be different from the rest of the KMER profile of the genome. So do you know if the KMER information binning helps or hurts for those kind of samples?
You mean the stream madness dataset?
Well, yeah, and I'm thinking specifically the binning uses both coverage and KMER profiles.
Yeah.
The KMER profiles helping or hurting for particularly.
Yeah, it's also a question. In actually, we run the experiment for the stream madness dataset. If we don't using the KMER frequency, actually we can get a better result, because for the stream madness dataset, the difference between different strains are very small. For the KMER feature, they are not very useful for distinguishing different strains. So only using the cartridge information actually get a better result.
Thank you so much.